Hello everyone. Let us continue section 14 on factor groups. In the previous class, we have seen theorem 14.1 in which we saw that if phi is a group homomorphism from a group G to G dash with the kernel of phi H, then you can see it as a onto homomorphism from G to phi of square bracket of G. And we can see that the collection of all cosets of H in G forms a group under the binary operation AH into BH is equal to ABH. Now this group is actually isomorphic to phi of square bracket of G under the isomorphism mu from G over H to phi of square bracket of G defined by mu of GH is equal to phi of G. We can now consider an example. So here gamma is a map from Z to Zn where gamma of M is the remainder obtained when M is divided by N. So if I denote Z with G, then we can have Zn to be gamma of square bracket of G since this map is onto. Now we can see that the identity element in Zn is 0. So the collection of all elements that are in Z which are mapped to 0 is the multiples of n in Z. So you have kernel of gamma is equal to nz. So if I denote it with h as in the previous theorem, we can now see that G over H is isomorphic to gamma of square bracket of G. That is Z over nz is isomorphic to Zn. Now we now call the cosets of nz as the residue classes modulo n. Now let us consider one more example. Taking n is equal to 5, in the previous example, we see that the cosets of 5z are, so 5z itself is a coset, and 1 plus 5z, 2 plus 5z, 3 plus 5z, and 4 plus 5z. How to add two cosets? As per our result, G over H forms a group under the binary operation AH into BH is equal to ABH, where AH is a coset of H in G containing A and BH is the coset of H in G containing B, and ABH is the coset of H in G containing the element AB. So to take the sum of two cosets 2 plus 5z and 4 plus 5z, we choose representatives, that is 2 from the first coset and 4 from the second coset. Since its sum is 6, you can find that the answer is the coset containing the element 6, that is 1 plus 5z. Similarly, to add 12 plus 5z and minus 6 plus 5z, you choose the coset containing 12, which is same as 2 plus 5z, and minus 6, which is same as 4 plus 5z. So the answer should be the same as the previous one. Next, we move to another section, factor groups from normal subgroups. In the previous section, what we saw is that a factor group G over H can be obtained by using a well-defined binary operation AH into BH is equal to ABH, which we obtained using a group homomorphism. Now what we are going to see in the next theorem is that this operation becomes a well-defined operation if and only if H is a normal subgroup of G. So let us see the theorem 14.4, which says that when H is a subgroup of G, then the left coset multiplication given by AH into BH is equal to ABH is a well-defined operation if and only if H is a normal subgroup of G. In order to prove this theorem, we first assume the condition given, that is AH into BH is equal to ABH, and we prove that H is a normal subgroup of G, that is AH is equal to HA whenever A is an element in G. Since these two are two sets, we use the standard technique, that is we first prove that AH is a subset of HA and then HA is a subset of AH. Now to prove the first part of this, we first initially assume that x belongs to H and then we show that x belongs to HA. So let us start the proof. That is, we start with the x belongs to H. Then since x is an element of this coset, you can also call it as xh. Now you consider another coset, that is A inverse H. So A inverse is an element of that coset A inverse H. If we take the product of these two cosets, taking the first coset as xh, then you will get it as x A inverse H. Now if you take the first coset as AH, then you can have AH into A inverse H is equal to A inverse H, which is same as EH, or it is H itself. Now since the left coset multiplication is well defined, you must have x A inverse H and H to be the same coset. But in order to hold this, x A inverse must be an element of capital H. That is, x A inverse must be some element small h, where small h is an element of capital H. So you can have x is equal to small h into small a, which means it is a member of capital H. Thus, we proved that AH is a subset of HA. Now, similarly, you can prove that HA is a subset of AH. For that, you need to start with x belongs to capital HA and end at x belongs to small a into capital H. So you can do it as a homework. Now we have AH is a subset of HA and HA is a subset of AH. Since A is an arbitrary element, this means that AH is equal to HA for any A in G, which means that H is a normal subgroup of the group G. Now, before going to the second part of the proof, let us see how the proof is given in your textbook. So this is the first part. Now, to prove the converse part, we assume that H is a normal subgroup and we prove that the coset multiplication given by the representatives is well defined. Note that since H is a normal subgroup, we can simply use the word cosets rather than the left cosets or right cosets. Let us start with considering the product of two cosets AH and BH. Since A and B are two usual members of these two cosets respectively, you can have AH into BH is equal to ABH. Now if you consider different representatives from the same cosets, we may choose AH1 and BH2 as two elements from these two cosets respectively, where H1 and H2 are members of capital H. Now if you take the product, we get AH1 into BH2 into capital H, and in order to prove that the coset multiplication is well defined, we need to prove that these two cosets are the same. Now if you consider the product AH1 into BH2, you can see that by associative property, you can write it as A into H1B into H2. Now H1B is a member of the set HB, which is same as BH since H is a normal subgroup. That is, you can replace H1B with the sum BH3, where H3 is an element of capital H. So modifying our product here, we can rewrite it as A into BH3 into H2, which is same as AB into H3H2, and clearly it is a member of the coset AB capital H. So thus we proved that ABH and AH1 BH2H are the same cosets, which means that the coset multiplication is well defined. Now, without much effort, we prove a corollary. Here, let H be a normal subgroup of G, and we need to prove that G over H forms a group under the binary operation AH into BH equal to ABH. So we already saw that this operation is well defined when H is a normal subgroup of G. So here we need to prove three properties, that is associative property, existence of identity element, and existence of inverse element. To prove the associative property, we consider three elements from G over H, that is AH, BH, and CH, where A, B, C are elements of G. Now if you compute BH into CH, you can see that it is BCH. So this becomes A into BCH. Similarly, if you compute AH into BH into CH, you can obtain it as AB into CH. Now, A into BC and AB into C are the same since ABC are elements of a group G. Thus, we prove the associative property. Now, what is the identity element in this group? You can see that EH is equal to H is the identity element since AH into EH gives you the element AH back. Also, you can see that the inverse of an element AH is A inverse H. So, if you multiply them, you can get EH, that is AH inverse is A inverse H. We have now completed the proof and we call this group as the factor group of G by H. As an example, when Z is an abelian group, you can see that NZ is a subgroup of it and hence it is a normal subgroup. Since NZ is a normal subgroup, you can have Z over NZ to be the factor group of Z by NZ. We now continue this section in another video. Thank you.